example of least squares fitting in Maple. Let's fit this function f of x to 10 data points along y equals x squared as x ranges between 0 and 3. First, let's do an interactive solution, which is easy to implement and might have a little bit less of the data that you would extract from a least squares fit. We'll do that one next. So to begin, I'm going to drag this fitting function down and define it as a function. Then I want to make some data points, so I'm going to write 3.0 k over 10 and make a sequence of points, sequence in k, as k runs from 1 to 10. I will convert this to a list and this list to a column vector, and I will give this column vector the name uppercase x. Now I want to define the function y equals x squared, so I'm going to write g of x equals x squared and make this a function. Then to obtain the corresponding vector of y coordinates, I will use this notation and call this vector of y coordinates uppercase y. Now I want to draw a graph of g. So here's x squared, and I will bring up the plot builder, set the domain 0 to 3, and I think I will just accept that graph. Next, I'd like to plot the data points, so I'm going to type x, y, two names x, y, and use the same tool, this plot builder, to draw a graph of those points, and use these options to make the graph look a little better. I'll make the symbols be solid circles, make them slightly larger, and draw that graph. Then I'm going to copy this graph and paste it onto here, and so we have a graph y equals x squared and the data points that I'm going to use for this fitting problem. Now let's do the fitting through the tools of the statistics package, and the additional information that can be obtained is essentially a regression analysis. So let's begin by installing the statistics package. And then execute this fit command. So the fit command accepts the fitting function, the data vectors, the name of the independent variable, and then this option summarize the information about regression in an embedded form. So let's execute that command, and this is the embedded information. Here is the fitting function, repeated here as the model, and here is information about the coefficients. There are 6 coefficients, B0 through B5, an estimate of their values, standard error, t-scores, r-squared value, adjusted r-squared value, and some information about the residuals. And you can see here residual sum of squares, residual mean square, residual standard error, degrees of freedom, some other information in here. the full gamut of regression data would be all 20 of these pieces of information in this table. The table is split into two parts. For a linear problem like we have, all 20 of these pieces of information are made available. For a nonlinear problem, just these 8. So one way to get at and display this information is to assign all of it to a module. The name of the module will be M, and one makes the assignment by this output equals solution module option. So execute that command, and then one way to display it is to use this print mechanism, which prints the results of this module M, one item per line. So you can see there's a lot of information here. When you get down to something like variance covariance matrix, you see that the data is large enough. These numbers are hardware floats. They're large enough that each row of this 6x6 matrix folds. So it's a little bit difficult to see it as a matrix. So this might be a piece of information that you would obtain separately so that you can massage this matrix to a more readable form. And so all of this data is available either en masse or one at a time by simply asking for the specific piece of information. And then there's one other thing that can be obtained, and that's this graph that shows the fit with error bars at each point.